Hello friends, in this video I'm going to discuss some problems related to Lagrange's mean value theorem. Okay, let us consider the first problem. Discuss the applicability of LMVT to fx is equal to x 1 by 3 in closed interval minus 1 1. Here fx is x power 1 by 3. Therefore, f dash x will be 1 by 3 x 1 by 3 minus 1, that is 1 by 3 x minus 2 by 3, which is equal to 1 by 3 into 1 upon x 2 by 3. Okay, clearly which does not exist finitely at the point 0, and 0 is the in between point of this interval minus 1 1, which does not exist finitely at x is equal to 0, which belongs to open interval minus 1 1. This means fx is not differentiable in the interval minus 1 1. Therefore Lagrange's mean value theorem, that is LMVT, is not applicable in this particular problem. However, f of 1 minus f of minus 1 divided by 1 minus minus 1 is equal to f dash c implies f of 1 is 1 power 1 by 3, that is 1, and here minus 1, and here 1 plus 1 2 is equal to 1 upon 3 c 2 by 3. This implies this is 1 plus 1 2, 2 by 2 1. This implies c 2 by 3 is equal to 1 upon 3, that is c is equal to 1 by 3 power 3 by 2, that is this is equal to 1 upon 3 root 3. Okay, now this denominator is more than 1, therefore clearly this is less than 1. Okay, and therefore this c will lie in the interval minus 1 1, open interval minus 1 1. Okay, therefore the conclusion of LMVT holds, but conditions does not hold. Okay, this is less than 1, therefore c belongs to open interval minus 1 1. It is clear. Therefore we can say therefore we have this: the two conditions of LMVT are sufficient but not necessary. We can say this since here in this particular problem we have that two conditions are not satisfying here in this particular problem, but the conclusion holds. But the conclusion of LMVT clearly holds here. Therefore, we can say these two conditions of LMVT are sufficient, but it is not necessary. Okay, as was in Rawls theorem also, conditions were sufficient but not necessary. Means conditions are not necessary for conclusion to hold. Here also, two conditions are sufficient but not necessary. Okay. Now next, consider the next problem. Show that if x is greater than 0, then log 1 plus x is greater than x by 1 plus x, and hence prove that x inverse log 1 plus x decreases monotonically as x increases from 0 to infinity. From 0 to infinity. Okay, we have two parts to prove here. First part we have to prove this. In the next part we have to prove this. And hence prove this. Means using this part we have to prove this. Okay, we have to prove the two parts here. Now let us define the function. Let fx is equal to log 1 plus x minus x by 1 plus x. Okay. Then f dash x will be 1 by 1 plus x, derivative of logarithmic function, and here applying the product rule, quotient rule of differentiation here. This is 1 plus x into 1 minus x into 1, and this is equal to 1 plus 1 by x. This is 1 plus x minus x, that is 1 by 1 plus x whole square. This can be further solved as 1 plus x minus 1 divided by 1 plus x whole square. Okay, and this is equal to x by 1 plus x whole square. This is square function, it is positive, and x is positive given to us. It is greater than 0. Okay, now this function is continuous, this function is continuous. Okay, therefore fx is continuous in the interval 0 infinity. We have here now f is continuous and derivable when x is positive. When x is positive, since f dash x is coming out to be equal to x by 1 plus x whole square, nowhere it is becoming infinite or indeterminate form. That means f is derivable and continuous when x is positive. Okay, here given x is positive. Also from here we have f dash x is greater than 0. Okay, means Lagrange's mean value theorem is applicable here. F is continuous and derivable, and this is Lagrange's mean value theorem applicable here. And also we have this f dash x is greater than 0. Therefore, by Lagrange's mean value theorem, we have done in the previous video, we have done if f dash x is greater than 0 and f satisfies the Lagrange's mean value theorem, then we have the conclusion f is strictly increasing. We have done this. F is strictly increasing when x is positive. Okay. Increasing means what? When x is greater than 0, fx is greater than f of 0. Okay. When x is greater than 0, this means f of x is greater than f of 0. This is the meaning of increasing function, and f of 0 is equal to log 1 minus 0, that is 0. Therefore, we have f of x is greater than 0, and f of x is what? Log 1 plus x minus x by 1 plus x greater than 0. That is log 1 plus x is greater than x by 1 plus x. This is the first part we have to prove. Hence proved. Okay. And in the next part we have to prove x inverse log 1 plus x is decreases monotonically. Okay, now let us define the second function. Let capital Fx is equal to x inverse log 1 plus x. Okay, now this is equal to log 1 plus x by x, and f dash x is equal to, this is equal to x square x into 1 upon 1 plus x minus log 1 plus x, and this is same as x by 1 plus x minus log 1 plus x by x square. And this is my fx. This is nothing but my fx only. This numerator is my this minus fx, I can write this capital F dash x in this form. I can write this since fx is log 1 plus x minus x by 1 plus x. Clear? Now, now we have this f dash x is equal to minus fx by x square. Okay. Now, x is greater than 0 implies fx is greater than 0 by previous part. Therefore, this is positive, this is positive. F dash x is less than 0. Therefore, f dash x is less than 0. Okay. Therefore, by Lagrange's mean value theorem, this capital Fx satisfies both conditions of LMVT, and also f dash x is less than 0. Therefore, we have fx is equal to x inverse log 1 plus x decreases monotonically as x increases from 0 to infinity. Okay, clear? This is my this is by Lagrange's mean value theorem. Okay, clear it is? Now we come to the next part, next question. Now we consider third problem. Prove that x minus x square by 2 plus x3 by 3 into 1 plus x is less than log 1 plus x, and it is further less than x minus x square by 2 plus x3 by 3 for x positive. We have to prove this. Okay. Now let us define a function. Let f of x is equal to x minus x square by 2 plus x3 by 3 1 plus x minus log 1 plus x. Let us define our function fx as this. Now f dash x, derivative with respect to x, this is 1, this is minus 2x, 2 will get cancelled out, this is minus x plus 1 by 3. Now applying the quotient rule here, this is 1 plus x whole square, this is 1 plus x into 3x square minus x cube into 1 minus derivative of this is 1 upon 1 plus x. Okay, this is 3x square plus 3x cube minus x cube. Okay, now we will solve this, simplify this. This is equal to 1 minus x plus 1 by 3 into this is 3x square plus 3x cube minus x cube divided by 1 plus x whole square minus 1 upon 1 plus x, and this is equal to 1 minus x plus 1 by 3 into this will be 3x square plus 2x cube divided by 1 plus x whole square minus 1 upon 1 by x. Okay, now this is equal to, I can write here taking LCM as 3, 1 plus x whole square. Okay, now this is equal to 1 minus x here, and this is multiplied by 3 into 1 plus x whole square plus 3x square plus 2x cube minus 3 into 1 plus x, this, and this is equal to 3, 1 minus x, 1 plus 2x plus x square plus 3x square plus 2x cube minus 3 minus 3x divided by 3 into 1 plus x whole square, and this is equal to 3 This is 1 plus 2x plus x square minus x minus 2x square minus x cube plus 3x square plus 2x cube minus 3 minus 3x whole divided by 3 into 1 plus x whole square. Now this is equal to, this is 1 plus x, this is 1 plus x minus x square minus x cube plus 3x square plus 2x cube minus 3 minus 3x divided by 3 into 1 plus x whole square, and this is 3 plus 3x minus 3x square minus 3x cube plus 3x square plus 2x cube minus 3 minus 3x divided by 3 into 1 plus x whole square. Okay, now this 3 will get cancelled out, 3x will get cancelled out, 3x square will get cancelled out. Okay, that means we are left with minus 3 and 2 minus x cube by 3 into 1 plus x whole square. Okay, now it is given that x is positive, this square function is positive, x is positive, that means x cube will be positive, but we have a minus sign here, therefore this will be less than 0 for x greater than 0. Okay, this is clear. Now my f dash x is less than 0 and f satisfies both conditions of Lagrange's mean value theorem, and with that f dash x is also less than 0. This is also true. That means by Lagrange's mean value theorem we can say fx is strictly decreasing. Fx is strictly decreasing for x positive. You can say this by Lagrange's mean value theorem. And meaning of strictly decreasing function means what? When x is positive, we have fx is less than f of 0. Sign will get reversed. This is a meaning, this is a definition of strictly decreasing function. Therefore, also f of 0 is equal to 0. Therefore, f of x is less than 0. And f of x is what? This is x minus x square by 2 plus x cube by 3 into 1 plus x is less than log 1 plus x. Okay, hence first part is proved. Now same way we consider the next function. Now define next function as, now let gx is equal to log 1 plus x minus x plus x square by 2 minus x3 by 3. Okay, now same here also, first find the derivative. This is 1 upon 1 plus x, this is minus 1, this is plus 2x by 2, that is x, minus 3x square means minus x square here, and this is equal to 1 plus x here. This is 1 minus, or I can say this, minus 1 plus x minus x square into 1 plus x. Okay, and this is equal to 1 plus here minus 1 minus x plus x square minus x cube divided by 1 plus x. Now this will get cancelled out, this will get cancelled out. Okay, means we are left with here, this is 1 minus 1 and minus x cube divided by 1 plus x. This will get cancelled out. We are left with minus x cube by 1 plus x. Since x is positive, this is positive, this is positive, this is less than 0 for x positive. X is positive given to us. Okay, now g dash x is less than 0. Now by Lagrange's mean value theorem, gx is strictly, well, LMVT. Therefore, gx is strictly strictly decreasing for x greater than 0. Therefore, x greater than 0 will imply g of x is less than g of 0 and g of 0 is 0. Therefore, g of x is less than 0, that is log 1 plus x is less than x minus x square by 2 minus x3 by 3. Okay, this is the second part, hence proved. Same way we consider the next problem. Show that v minus u by 1 plus v square is less than tan inverse v minus tan inverse u is less than v minus u by 1 plus u square if 0 is less than u less than v, and also deduce that pi by 4 plus 3 by 25 is less than tan inverse 4 by 3 is less than pi by 4 plus 1 by 6. Okay, now consider this problem. See here, this problem is very, very important. In this problem, we have to show that this inequality holds, and also from this inequality, we have to further prove this inequality also. First, we have to prove this, and using this inequality, we have to prove this. Okay. Now, we define the function. Let f of x is equal to tan inverse x. Since we are having tan inverse in this problem, therefore we define our function in this form. Then f dash x will be equal to 1 upon 1 plus x square. Okay. Now we consider fx is equal to tan inverse x, and we consider the interval uv. Okay. Now f is continuous in closed interval uv. Okay, u is positive here. Okay, f is continuous in the interval uv, and same way f is derivable also in uv. Therefore, by LMVT, there exists a real number c in the open interval uv such that f dash c is equal to f of v minus f of u by v minus u. Okay, that is tan inverse v minus tan inverse u divided by v minus u is equal to 1 upon 1 plus c square. Mark this as equation number 1. Okay. Now, c lies between u and v. Okay. That is c is greater than u. Okay. This means 1 plus c square is greater than 1 plus u square. And this will imply 1 by 1 plus c square is less than 1 by 1 plus u square. And same way, since c is less than v, this means 1 plus c square is less than 1 plus v square, and 1 upon 1 plus c square is greater than 1 upon 1 plus v square. It is clear, this and this. Okay. Now combining these two, we can say, we can write as, therefore we have 1 upon 1 plus v square is less than 1 upon 1 plus c square is less than 1 upon 1 plus u square. Okay. Now substituting this value 1 upon 1 plus c square using the equation number 1, this is equal to tan inverse v minus tan inverse u divided by v minus u less than 1 upon 1 plus u square using equation number 1. Clear? I can write this as this. And this implies v minus u by 1 plus v square is less than tan inverse v minus tan inverse u is less than v minus u by 1 plus u square. Okay, first part is proved. First part is proved. And in the second part, we have a term like, in second part, we have a term like tan inverse 4 by 3 and pi by 4. And we know tan inverse of 1 is pi by 4. Tan pi by 4 is 1. And we have a term like tan inverse 4 by 3 and pi by 4. Therefore, we will take the interval as, we will take u and v as pi by 4 and 4 by 3. Okay. In order to prove the second part, we take u as 1 and v as 4 by 3. Okay, since we have pi by 4 term and tan pi by 4 is 1 and we have a term of like tan inverse 4 by 3. Therefore, we have to take u and v in this form. Okay. Also, we know 0 is less than u less than v. Okay. Now, this will imply here v is 4 by 3 minus 1 divided by 1 plus v square, that is 1 plus 16 by 9, and this is tan inverse 4 by 3 minus tan inverse 1, that is pi by 4, and it is less than 4 by 3 minus 1 divided by 1 plus u square, that is 1 plus 1. Okay, clear? We are getting here like this, and this is equal to, this is 4 by 3 minus 1, that is 1 by 3 here, and here 25 by 9. Okay, 25 by 9 here, and this is less than tan inverse 4 by 3, and this tan inverse 1 is pi by 4, tan pi by 4 is 1, and it is less than 4 by 3 minus 1, that is 1 by 3, and here we have 2. Okay, now simplifying this, we get this implies 1 by 3 into 9 by 25 is less than tan inverse 4 by 3 minus pi by 4 is less than 1 by 6. That is, this is equal to 3 by 25. Now, adding pi by 4, this is plus pi by 4 is less than tan inverse 4 by 3 less than 1 by 6 plus pi by 4. That is, we have pi by 4 plus 3 by 25 is less than tan inverse 4 by 3 is less than pi by 4 plus 1 by 6. Okay, hence the second part. Okay, hence proved. This is how we have to solve the problems related to Lagrange's mean value theorem. Okay, that's it for this video. If you have any queries or any suggestions, please write to me in comment box. Thank you.